Earth teems with life. Even here in the Arizona desert, shady nooks conceal diverse plants, and many species thrive in this hot, dry environment. Life is shaped by influences from beyond Earth, by the light and heat of the sun, of course, but also by rare, sometimes catastrophic events. Our journey begins with one such event in the story of life. We are looking at a magnificent scar on Earth's surface, a crater that formed almost 50,000 years ago when a visitor from space collided with our planet. That visitor was an asteroid that vaporized on impact. It explosively, instantaneously formed what we now call Barringer Crater. Asteroids and comets have collided with our planet throughout its history. They have changed the course of life on Earth, and they may have brought the ingredients of life to our planet billions of years ago. An asteroid about 30 meters across created this kilometer-wide crater. When that metallic space traveler struck Earth, it devastated the local environment. Geological activity erases almost all evidence of these impacts, but we have identified nearly 200 impact craters dotting Earth's crust. We studied the geology around these craters to determine when the impacts occurred. They range in age from thousands to millions to billions of years old. The age of one crater implicates it in a global calamity that took place 66 million years ago. We can't see it as clearly as the crater where we started our journey. But tiny variations in Earth's gravity around Mexico's Yucatan Peninsula reveal underground concentric rings, the largest nearly 200 kilometers across, Chicxulub Crater. An asteroid about 10 kilometers in diameter caused this damage. The impact ejected debris that fell to Earth for hours, with hot rocks raining down around the globe. The initial burst of energy and the firestorm of secondary impacts superheated Earth's atmosphere. Soot darkened the skies for months, interrupting photosynthesis and cutting off the food supply for innumerable species, including most dinosaurs. We find geological evidence of this event all around Earth in a global layer of dark clay that bears an extraterrestrial chemical imprint. A city-sized visitor from space 66 million years ago changed the story of life. To learn more about these visitors to Earth, we have sent spacecraft to explore asteroids and comets. Let's follow them to this final frontier. Astronauts have only traveled as far as our nearest neighbor in space, the Moon. But our robot explorers have voyaged throughout the solar system. We learned the planets' names early in life: Mercury, Venus, Earth, and Mars. Along with the giants, Jupiter, Saturn, Uranus, and Neptune. But we have many other fellow travelers around the Sun, including rocky asteroids and icy comets. Left over from the formation of the planets, these little guys hold secrets to the origin of our solar system. Cool comets reside far from the Sun, but most asteroids orbit between Mars and Jupiter. Let's visit Vesta, an asteroid responsible for many impacts on our planet. We can think of Vesta as a building block that could have combined with others to form a planet, a lingering remnant of our solar system's formation. NASA's Dawn spacecraft orbited the 500-kilometer-wide asteroid for more than a year. Dawn discovered that water may have flowed briefly on Vesta's surface, which fits with the idea that asteroids or comets may have brought water to Earth billions of years ago. Vesta's devastated South Pole shows evidence of a major collision that took place about 1 billion years ago. It excavated quadrillions of tons of rock and debris. Fragments from that collision have made their way to Earth. About 1 in 20 of all meteors that fall to Earth originally came from this one asteroid. Vesta is one of the largest asteroids. Only a few hundred asteroids have diameters greater than 100 kilometers. City-sized asteroids are far more common. If we look for asteroids 10 kilometers in diameter or larger, we expect to find about 10,000 in the asteroid belt. Medium-sized asteroids with diameters greater than 1 kilometer number nearly 1 million. And perhaps hundreds of millions of asteroids are smaller yet. Let's visit one of these smaller ones. Little Itokawa travels closer to the Sun than most asteroids. It's just over half a kilometer long, about 6 football fields. A rubble pile held together by weak gravity. Itokawa was likely born in violence, the product of an ancient collision. Itokawa began its life farther from the Sun. So why did its orbit change? Although tethered to the Sun by gravity, asteroids also experience smaller gravitational tugs from the giant planet Jupiter. And they respond to the Sun's warmth by changing their rotation and speed. These influences cause asteroids' orbits to change slightly, sometimes sending them hurtling toward the inner solar system and Earth. We know of tens of thousands of these objects. We call them near-Earth objects, or NEOs, even though most of them don't get anywhere near our planet. Itokawa and other NEOs formed in the main asteroid belt between Mars and Jupiter, but they got nudged closer to the Sun over many, many orbits. Some comets have migrated in from even greater distances. Mere decades ago, an encounter with Jupiter diverted Comet 67P, Churyumov-Gerasimenko, nicknamed Chury, into an orbit closer to the Sun. This made Chury an accessible target for the Rosetta spacecraft. In November 2014, Rosetta released a washing machine-sized lander called Philae to touch down on the comet. After a bumpy landing, Philae detected the precursors of molecules important for life. From orbit, Rosetta also found that water molecules evaporating from the comet differ slightly from those we find on Earth. They don't match. If our planet's water came from space billions of years ago, it may have arrived on comets, but not comets like Chury. Comets originate far from the sun in the deep freeze of our solar system. Chury probably came from beyond the orbit of Neptune, the most distant planet. We have discovered more than 1,000 such icy worlds. The most famous of these? The ever-popular dwarf planet Pluto. When we look at Pluto's orbit, we see something wildly different from the planets in our solar system. Its orbit appears stretched and tilted. And Pluto revolves around the sun twice for every 3 times Neptune does. This perfect ratio kept it from getting kicked out of the solar system altogether. Other objects were not so lucky. More on that in a moment. First, let's take a closer look at Pluto. We visited Pluto in 2015 thanks to NASA's New Horizons spacecraft. The orbits of Pluto's 5 moons resemble a bullseye, suggesting that they formed together in an ancient collision. New Horizons sped through the target, focusing on Pluto and its moon, Charon. From Pluto's nighttime side, New Horizons observed sunlight streaming through a thin, hazy atmosphere. Pluto's diverse terrain includes towering mountains of water ice and slowly flowing glaciers of frozen nitrogen. Charon, too, has a varied terrain and a vast chasm from which water appears to have erupted and frozen onto the surface. We will learn much more from our brief visit to the Pluto system, but strange as it sounds, we have already learned something from the way it orbits the sun. If we look at the orbits of Pluto and its many neighbors, we find evidence for a violent rearrangement of the planets. All the places we have visited tell us different parts of the same story. A story that began 4.6 billion years ago with the birth of our solar system. After the sun ignited, most of the material around it had flattened into a disk. We have used computers to simulate what happened inside the disk. Here, a dense swarm of objects collided with one another. Some stuck together to form what astronomers call planetesimals. Pulled together by gravity, some planetesimals formed the planets. Others became asteroids and comets. As the planets grew, they carved out gaps in the dusty disk. If we look at the orbits of the planets and move time at warp speed, So 1,000,000 years pass by every 10 seconds. We can watch how the debris cleared. We've seen how small objects such as Itokawa and Chury can migrate through the solar system. But even the giant planets shifted orbits in the past, causing gravitational havoc. Many unlucky asteroids and comets and dwarf planets got kicked out of the solar system altogether. A few, including Pluto, settled into orbits that allowed them to coexist safely with the planets. And many tiny objects scattered through the solar system, cratering the surfaces of the inner rocky worlds. We call this burst of chaos the Late Heavy Bombardment. Once things settled down, about 3.8 billion years ago, the orbits of the planets stabilized and a much less cluttered solar system remained. Earth back then looked very different. The constant stream of objects hitting Earth may have brought surprisingly fragile but life-crucial chemicals along with them, including water, nitrogen, and carbon dioxide. That chemical payload may also have included complex organic precursors of life, or perhaps those compounds formed in collisions. Our planet became a laboratory for complex chemistry to develop. Life seems to have begun on Earth as soon as the bombardment ended. In fact, impact craters may have provided places to kickstart the chemistry of life. We can see similar impact evidence on the ancient Moon. If we fast forward through time from the end of the Late Heavy Bombardment to the present, we can watch as the Moon's cratered surface is covered over by its familiar mare, vast pools of dark lava covering its surface. Occasional infrequent impacts continue to scar the Moon's surface. The largest leave behind bright craters and long streaks. We see the Moon's history written on its surface. Earth has suffered even more impacts than our sister Moon, but has erased the scars that show it. And however violent our history, it could have been worse. The migration of the icy giants and ensuing chaos of the Late Heavy Bombardment likely cleared the solar system of many dangerous objects. Instead of a steady stream of life-altering impacts on Earth, we rarely experience major events. However, small visitors from space arrive all the time. We detect airbursts caused by asteroids. Over more than a decade, we have cataloged hundreds of them peppering the globe. Measured in equivalent tons of TNT, these explosions ranged in size from a few tons to hundreds of thousands. The most powerful of these bursts took place on February 15, 2013, over the Russian city Chelyabinsk. Almost 20 meters in diameter, a stony meteor entered our atmosphere at a shallow angle, leaving a trail that stretched more than 100 kilometers. When the main part of the meteor fragmented, it created a burst of light brighter than the sun, and a shock wave that took almost a minute to reach the ground. As the meteor slowed and continued its gentle arc toward Earth's surface, that shock wave shattered windows and damaged buildings in the places highlighted here. Nearly 1,500 people sought medical attention in the next few days, mostly for injuries from shattered glass. We can compare the size of the blast to the area of metropolitan New York City, or the San Francisco Bay Area, or Greater Tokyo. No one saw the Chelyabinsk meteor coming, but these events occur all the time. So, how can we avoid being surprised in the future? We have developed plans to deflect or destroy incoming asteroids, but we need to find them first. To date, we have discovered only a few percent of the near-Earth objects larger than the Chelyabinsk meteor. Our current map of the inner solar system looks crowded enough, but we estimate we will find 100,000 more NEOs. One proposed mission, Sentinel, dedicates a privately funded space telescope to search for NEOs. Scanning in infrared light, it will see asteroids warmed by sunlight. Sentinel should spot 90% of NEOs with diameters greater than 100 meters. On Earth, many telescopes catalog the locations of asteroids and NEOs, and we are finding them faster than ever. But the task demands diligence. A project under construction in Chile, the Large Synoptic Survey Telescope, will survey the entire sky every few days. Its frequent observations and extraordinary sensitivity will allow it to detect faint moving objects, including asteroids and NEOs. Once we find these objects, we study them. They tell us about our past, where we came from, why Earth remains a special place for life. When you gaze up at the scarred face of a full moon, you can reflect on the eons of impacts etched on its surface. And when you spot a meteor streaking through the sky, you can recognize a tiny cousin of the objects that influenced life on Earth long ago. In these moments, we look to the past and glimpse the future, recognizing life's deep connection to the universe around us.